Welcome to Walkabout the Galaxy, the friendly astronomy podcast where the science is universal, the opinions are personal, and the weather outside is frightful. We are Strange Charm atop the Astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney.
Coming to you from the storm-ravaged Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. We are also at www.walkaboutthegalaxy.com, where you can see how to order a Walkabout t-shirt. You can also reach us at wtg@ucf.edu or with hashtag AskWTG. Our stumper today is temporal.
Nice.
And it's very simple. If you, right now, we had a beautiful launch this week.
It was very pretty.
Very, very nice light show from the Inspiration 4 launch. Mm-hmm. And so there's...
I have a bone to pick about that.
The launch?
Yes.
What?
I live like 5 miles west of you, Josh, and I saw your pictures of that thing, and we saw none of that because there was a cloud that just happened to get in the way.
Yeah, we had great views.
I live like a mile from you, and you son of a gun.
Hey, what can I say?
I know. I'm not mad with you guys. I'm just mad with weather.
Nature.
Yeah.
The upper atmosphere.
Yeah. I mean, we saw a fair portion of it. It was great, but
it was really spectacular. But yeah,
anyway.
To the launches, it's because just after sunset, then you get these very high altitude, beautiful light shows of the exhaust illuminated by the sunlight.
Yep.
You could see both stages. It was really cool.
Yeah, you could see the maneuvering thrusters from stage 1 as it was steering its way back down.
Yeah,
that was very cool.
That was really awesome.
Wait, you could see that, but not the plume?
That's right.
I don't understand.
When it got lower is the only time you... Anyway, it was a whole thing. I don't know.
Okay.
Clouds. What are you going to do?
You're going to move closer to the coast.
There you go.
Space coast.
There you go.
If you were one of those people, if you were selected to go for a ride like the 4 lucky folks...
Oh, right, we're on Stumper, not...
...who are on Inspiration 4...
Yeah.
Mm-hmm.
They're going on a 3-day mission. We're actually recording this about 48 hours after they launch. They've got another day or so in orbit. And it's a high orbit. They're higher than the space station. Jeepers. I'm getting choked up just thinking about it.
Yeah, it's on a high orbit. It's pretty cool.
That's a cue for me to shut up and ask you guys a question, which is, how long would you want to be up there in that kind of a ride with 3 other people, not your family? You're in a fairly small capsule, okay, big by Apollo standards, but small, with 3 other people in that cabin doing all your business, orbiting the Earth, which is spectacular. How long do you want to be up there?
1 day.
24 hours?
24 hours, that's it.
Yeah. Well, really, I want to come down to go to bed, so like 18 hours, something like that, yeah.
You don't want to have to be sleeping in that?
I don't know, because you're sleeping, you're not really experiencing, I don't know, maybe a sleep would be fine, but no more than 1day. Okay. No more than 1 day. You get, because like you experience it. It's amazing. It's awesome. And then...
I've had enough already.
Yeah.
Okay.
Yeah.
So what you say when your folks come to visit?
Yeah. Oh, yeah.
Like they come in from out of town and they visit, you have lunch and dinner, and they're like, okay, that's enough already. Enough. Can you guys go home?
Yeah. Because, like it is, I've been at that capsule looked pretty darn small, like for 4 people, no privacy and all that business. But
right.
They probably put up a curtain occasionally.
I would imagine there's a curtain or for some sort of bathroom activities.
Maybe.
Anyway, how long would you want to be up there, Eddie? 10 years?
No. In the capsule, maybe a week.
A week?
A week?
Yeah.
What are you going to do with yourself for a week? You want to be up there
long enough to get sick of it. Is that right?
I don't know that. I mean, I think I would. Yeah. I mean, I think I would get tired of being in that small a space with that many people.
Uh-huh.
But I just feel like there's going to be different things to see and do. They're doing experiments in science up there.
Ooh.
They're there's going to be different views as you go around the Earth, right?
Right, but you go around the Earth every hour and a half. I mean, obviously the orbit slowly,
rotating.
Right? Yeah, obviously you see somewhat different things, but
Okay.
But I think longer than a week. The things like the bathroom, like after about a week, you're gonna have to. You're gonna have to
go at least,
to the bathroom after about a week. So
After about a week. Okay, let me take a note of that.
but like some sort of nice shower. I do love a good shower, so that's gonna be that's my one big hang up with most of space travel right now.
All right. Well, today we'll talk about quasars, space dust, and impactors. But first, this episode of Walkabout the Galaxy is brought to you by Calabi manifolds.
whoa.
If you're feeling lost in your walk about the multidimensional space-time continuum of superstring theory, then maybe you should pull a Calabi manifold as a map out of your six-dimensional pocket. After all, with the Ritchie flatness and a vanishing first churn class, the Calabi manifold is the ideal solution to your geometric dilemmas. And if you feel daunted by its multidimensional complexity, just remember that the canonical bundle of the manifold is trivial. So whether you're trying to fit the universe into 11 dimensions of space-time or maybe working on a new Marauders map, Harry Potter shout out, try a Calabi manifold. Calabi manifold, all the dimensions that's fit to print.
Wow.
Yeah, I feel like in your other life, you're a high energy physicist.
Oh, really?
Yeah.
They just have the most fun names.
They do. They have cool
fun
stuff.
names and terms and things like that.
Yeah.
All the news fit to print.
That's right. I just, I'm not, there's nothing I can find that fits Calabi manifolds.
No. Which is...
Yes. Go with the obvious.
New York Times? Okay.
Yeah.
Yep. So, speaking of news in the New York Times, in addition to Inspiration 4 space news, there's some Artemis news. This is related to the long-running feud between...
Sort of, yeah.
Between who?
Blue Origin
Blue
and SpaceX and NASA.
SpaceX. Yeah, so there's... NASA has a bunch of has had a bunch of open contract calls. Sort of the big one that we've talked about numerous times on here was this call for the human landing system for Artemis.
Like the first land.
For the first landing. Yeah, and it was like maybe some after that, but it's definitely for the first landing. And NASA, there were 3 big companies competing in that one. It was SpaceX, Blue Origin National Team, which included a bunch of different organizations, and then another one led by Dynetics. And that one, controversially, slightly, SpaceX was the only one chosen, which is a little surprising because NASA has been funding typically multiple to move forward and compete a little bit and blah, blah, blah. And Blue's been suing about that. But like in the meantime, there's been this other call that's been open for additional landing systems, and like moving forward for additional contracts. So there's what's called Next Step 2. There was an announcement for some milestone-based contracts to like develop landers and show they'll do milestones. And they recently, just this week, I think, last week, selected teams to develop lander concepts and like further these concepts. So it's like pretty early stage development.
Yeah, so fairly, compared to like the SpaceX selection, which was a few billion dollars, this is in the low tens of millions of dollars. Is sort of like, here's some money, keep doing your pencil paper kind of work.
Yeah,
and it includes Blue Origin, but it also includes separate awards to some of their national team members.
Yeah,
right, which set off a sort of flurry of speculation about what that might mean.
Yeah, so
I don't think it means anything.
So Blue, Dynetics, Lockheed, Northrop Grumman, and SpaceX all got contracts. SpaceX was only $9 million. Blue was 25 million, and the others were all a little bit bigger.
And Northrop and Lockheed were part of the national team with Blue Origin.
Yeah. So I mean, they're all. So it's different than the actual lunar landing demonstration that was awarded previously. But they are all funding to continue to develop performance and design standards, meet requirements, look at safety, all that kind of stuff. So it's a good step.
Right.
And important.
Yeah. There was we mentioned previously some of these Zooniverse projects, citizen science projects, and there's an interesting even with the proliferation of these big automated survey telescopes and things like that, there's still wonderfully the occasional discovery or observation that's made by amateur astronomers with their backyard telescopes. That's just one of the cool things about astronomy is there's a lot of sky to look at, and things are always changing.
Yep.
And we're not at the system where there's a professional grade automated computer controlled telescope pointing at literally every single
at all
thing
times.
in the sky
Right.
at all times.
Yeah.
Right? So astronomers discover comets, and in this case, an amateur astronomer, caught video of an object hitting Jupiter.
Watch out. Is Jupiter okay?
Jupiter's just fine.
Great.
Yeah.
Who knows? Maybe the Jupiter atmospheric blob beasts that lived right there are in trouble.
Some locally.
Yeah.
If somebody was there locally, they had a bad day.
Yeah.
Because there's a lot of energy. It was a pretty significantly sized flash.
Right. I mean, obviously, it's visible from Earth.
Right. Yeah, with a modest telescope.
Right.
So that's cool. He's got a little video. You see this little flash appear.
Yeah. I haven't. It was a few days ago. I haven't looked to see if there's been any follow up to see any additional long duration, like
see
a
if
few
there's
days. Sometimes you
high
see
resolution.
streaking.
See traces of it in the atmosphere.
It looked. When I was reading it, it sounded like there wasn't any of that. Yeah. Like that it was a small enough thing that even an hour later it was undetectable.
You couldn't see anything. It's interesting because famously almost 30 years ago, the Shoemaker-Levy 9 comet, which had broken up into a bunch of different impactors, and they slammed into Jupiter over the course of several hours. And those weren't particularly huge chunks. They were kilometer scale objects, I think. And they left these very visible scars, or scars is maybe not the right word, but they changed the chemistry of the atmosphere in some ways that left visible markings in it for a long time.
Right. Right. That probably has to do with like how deep into the atmosphere these things penetrate. If they're dredging up stuff from lower in the atmosphere, this thing probably burned up
and
really high in the atmosphere, and so made a big flash and then was gone.
Yeah.
Fun.
But it's awesome.
Yeah.
He happened to be, videoing it right at the time when it happened, so that's great.
Well, speaking of things running into things, flying around in the solar system, that brings us to our first topic, which involves one of Addie's favorite
Dust.
things.
Dust!
Space dust.
Space dust.
Yay. So I was looking around at recently published articles, and this one caught my eye because it was about dust. So there's a new article out by a group of folks who are involved in the PSP mission.
Parker Solar Probe.
Ooh, yeah.
So Parker Solar Probe, just as a reminder, right, is a solar mission. So it has a number of instruments that are intended to study the solar wind and the sun.
This is that one that has that orbit that brings it pretty darn close to the sun sometimes.
Yes.
Yeah. So it's going to be super close to the sun, and it's going to be super fast moving when it does it.
Its closest approach has 24 orbits of the sun. And it's using Venus to gradually lower its perihelion, its closest approach to the sun. Mm-hmm. It's going to get down to 9.8 solar radii.
That's so close.
That is so close.
That's less than 10.
That's toasty.
That is so close.
That's very close to the sun. How close is Mercury?
Mercury is about 60.
Yeah.
We're about 200.
Yeah.
60 or 70 or so for Mercury.
Yeah.
So
very close. It's going to be quite toasty.
It will be warm.
But they're going to be zoomy when they're doing that.
They will be traveling very fast.
Very fast. So PSP had to be designed to withstand that environment. But it has, and generally it's looking to understand the energetics of the corona and the solar wind, so those outer layers of the sun. So it's actually like trying to get down into those regions and look at the structure of the solar wind and look at energetic particles. But to do that, it has what's called the Fields instrument, which is basically 4 or 5 antennae that stick out from the spacecraft. If you're watching on video, my arms are sticking out really wide right now.
Long metal rods.
Yeah, right.
Basically,
so they're
right?
fancy, right? So it turns out to do like radio antenna and electric field antenna. You just need to stick big long metal rods out.
Right.
They're calibrated metal rods, and in that way you can detect potential spacecraft. You could detect the potential on the rods, look for electric fields and things like that. And it measures, generally it measures the electric field around the spacecraft. And it looks like, and so it can look at like different places in space, depending on which direction it's facing. It can give you some directionality based on which direction the spacecraft is facing. And one of the cool things people have done for a long time now, I think since Voyager, actually.
Yeah.
Was that the first
so.
time we did it?
Yeah.
Is look for dust using these types of electric field instruments.
What? How you do that?
Yeah. So it turns out when things are flying through space, they get hit with dust, usually.
Yeah.
And when the dust impacts, it basically vaporizes and it creates a little mini plasma that then sort of spreads out and modifies the electric field of the region surrounding the spacecraft.
So you get this little, you get a little blip signal from these antennas.
Yeah.
And I believe, I can't remember now for sure whether or not the Pioneers 10 and 11 saw this. They had their own dust detectors, but definitely on Voyager, they observed these blips and they weren't looking for it. And then they were like, saw them and they're like, oh, you know what this is? It's little tiny particles hitting, vaporizing, and some of the plasma, some of those charged particles then are collected on the antennas. And they did all this work to like try to calibrate this. Like the spacecraft is your instrument, but it wasn't designed to do that.
Yeah.
So they do all this fancy modeling, and actually at your advisor's lab in Colorado, they built a little model because Cassini, which had a dust detector, but it also had this phenomenon.
It had electric field, yeah.
They made a little model of Cassini and stuck it in a dust impact lab and shot things at it to try to sort of calibrate.
Really?
Yeah.
Where it would see the things.
Where what its sort of effective area was for impacts detection.
And you can imagine if you have these 4 different antennae that are sticking out sort of all perpendicular to each other, they are at
you need to get your legs involved here.
I know.
There's 4.
They're under the table. You can't see it. Doing star pose. You can get a little bit of directionality because you can see like, oh, it shows up on this antenna first, and then we see it on this antenna and this antenna.
Yeah. Voyager 2 was the first.
Yeah. Yep.
So Parker Solar Probe has seen this, I'm guessing.
It has, yes. So, and they've done it more recently with stereo. There's been a bunch of analysis of stereo, which is another solar instrument. But so PSP has seen this effect. And so there's a new paper out looking at some of where they're seeing these impactors. And so they model sort of like where PSP is in its orbit and which direction they think the dust impacts are coming from. And they see interesting and then they model what the hit rates are from dust impacts to try to look for these different populations, because we know there are some populations of like meteors and meteoroids in different orbits that it's been passing through as it's approaching the sun.
The sort of distribution of small particles in the solar system, dust, what we call dust, just means really small particles, is interesting, and it has a very interesting relationship with the sun. It's sort of like a come here, get away kind of relationship. It's like a love-hate relationship between dust and the sun, because for bigger particles, sunlight removes angular momentum from those particles through various effects. So the interaction of the momentum of the sunlight on orbiting particles causes their orbit to decay. But when they get in close to the sun, they get so hot that they start evaporating. Even if they're rock, they start evaporating. And when the particles are small enough, they can become something called a beta meteoroid, where the solar pressure on the particle exceeds the gravitational attraction from the sun on the particle, and they are then
out. I've never even heard of that.
So you have this. You can have this. You can have the same particle sort of like being pulled in by the sun through something like Poynting-Robertson drag. And so orbit spirals in, but then if it gets in close enough and it becomes smaller, then it reaches this critical size where it then starts spiraling out again as a baby.
Yeah, and then the alpha populations, I forget what the source of those is.
I don't know that. I don't know that term. Yeah.
There's alpha and beta meteor, right? They wouldn't have just started with beta.
Oh, I don't know the alphas. I thought it was beta meteoroids because they use the Greek letter beta equal to the
Oh,
ratio
maybe.
of the radiation pressure divided by the solar gravitational
Maybe
force.
I'm saying it wrong.
But in any event, that's one of many different funky things that can go on with the interaction between sunlight and these dust particles. And so now we have a spacecraft in there that's actually sampling that population, that because it's very hard to see this stuff when you're looking towards the sun. We see dust, the zodiacal cloud, most easily sort of looking
sort of just off.
Yeah, so I guess I was going to say something stupid.
Oh, don't do that.
Not for the first time
Yeah.
or the last time, unfortunately.
But you caught yourself.
I did catch myself.
Okay.
You do see small particles when you look towards the light source.
Yes.
Yeah. But now we got a in situ detector.
Yeah, so it's looking at sort of the hit rates, right? So how often it's getting hit with these particles and like where those are in the orbit.
And it's flying around on its own complicated egg-shaped
Yeah, so
orbit.
it's a very elliptical orbit. So it comes in toward the sun, and you sort of, it's a complicated thing. So you'd think like, oh, when it's passing right through the densest part is when you would have like the peak, but it's a little bit different because like where it is in its orbit, it's actually then going a similar speed to those particles.
Oh, yeah.
So the hit rates are actually going to go down when you're closest to perihelion for the orbit. And so you see a spike just before perihelion in a lot of these, and then just after. But then they're actually, and that sort of represents those populations they expect to find.
Yeah.
But they're also seeing a spike at a little bit different point in some of the orbits. And they think it might be due to another population of these meteoroids.
That might be coming from some big object that maybe we don't know about or haven't seen or something.
So there's a hypothesis from the folks who worked on this paper that it's this Geminid meteor stream that might be associated with Phaethon. So there's been some newer work that there's maybe a potential Geminid meteor stream, and it's interacting with those. But it could be, there's enough uncertainty in the data that it could be a little bit of something about the way the orbit is. It could be some additional signals they're not picking up on correctly.
Right.
But it could be an additional population that they're seeing.
New source of what we call parent bodies. Mm-hmm. So that's exciting. Yeah, that's one of the reasons. I mean, I did dust stuff too in my grad student days and since, but especially in my grad student days. And the thing about dust, like why we get excited about it, is that it's a great tracer of things that you can't otherwise easily see.
Yeah.
So that's cool. Well, speaking of things running into things, it's a segue to our
like
trivia.
to do that.
We do that.
Yeah.
We do our experiments in our research. And now in our trivia is about things running into things. And so it relates very much to what we were just talking about
Excellent.
with this topic about impactors. We mentioned the Colorado Center Dust Accelerator.
Yes.
That Mihai Haranyi leads, where they accelerate little tiny dust particles and run them into things to learn more about, among other things, just the exact process you were talking about, little tiny dust particles hitting spacecraft at very high speeds. And the trivia is about what are those speeds like? So you have several different speed questions here.
Oh, man, I should really know this.
And I'm just going to give you a couple of sort of reference points about some guns and
Speeds.
things. So like the fastest, I think, at that Colorado impact experiment, they accelerate little tiny, very small dust particles up to close to 100 kilometers per second.
They get pretty fast on some of them.
60
Most of them are a
miles per
little bit
second.
slower.
Most are less than that, and that's sort of a couple tens of kilometers per second, but still very fast. The Ames vertical gun facility shoots larger projectiles. The gas accelerates it down. They study sort of like impact cratering and shattering stuff.
I think we talked recently about
We talked about their experiments about like nudging
guns.
asteroids using data from that. And their impact speeds are like 7 kilometers per second. A regular gun that's used to kill things shoots at about 0.4 kilometers per second. Here are your speed questions.
Okay. 88 miles an hour.
Wrong.
Oh.
How fast was the fastest meteoroid whose speed has been determined going when it hit the Earth? Okay.
Solid Earth?
No.
Okay.
I mean, before, no. On its way in, so based on,
Intercepted with Earth's orbit.
yes, on its way into the atmosphere, on impact or entry into the
relative
atmosphere.
to the Earth.
Speed
Yes.
relative to the Earth. How fast was that going? And then related to that, what's the slowest speed that it could have been going if it was an interplanetary impactor? And what's the fastest speed that it could have been going if it were an interplanetary
Oh, man. I used to
impactor?
know these numbers.
Yeah. Okay. And then the bonus trivia will be, what's the fastest non-dust bullet that has ever been fired by a device, a gun like device? And it was for science.
For science.
It was, as it happened, it was for science.
But it's a macroscopic thing.
But it was a gram. I will tell you that the mass of it was 1 gram.
Oh, precisely.
I'll also tell you that the length of the gun was 60 feet.
Wow.
That's a big gun.
And it was from Sandia National Labs.
That checks out.
Okay, so those are your speed questions.
That's going to make me.
How fast was the
look
fastest
dumb
one
later.
going? How
I should
fast
know
it
those.
at least must it have been going if it was an interplanetary impactor?
Yeah.
And how fast could it possibly be going and still be interplanetary
Okay.
instead of interstellar
Right. Obviously.
or intergalactic?
Interstellar could be going at an arbitrary. Okay.
Arbitrary speeds, right? Okay. So speaking of intergalactic,
Yes.
the segues are just, it's that kind of
Oh, the Beastie
Rolling
Boys.
off yeah.
It's one of their best songs.
That's the song I always
what
pick when
is?
I do the rock and roller coaster.
Intergalactic.
That's a Beastie Boys song?
It's, yeah.
Yeah.
Okay.
Good one. Anyway.
You know what I'm talking about when you do the roller coaster at Universal that has the sound that plays?
The rock and roller
The
coaster?
rock and roller coaster. I always pick that song.
Oh, it's
nice.
called Intergalactic.
I think so. It might have a longer title, but that's part of
What's the genre of the Beastie Boys?
it. Rock, alternative,
Rap. Rock.
Rap?
It's not.
It's kind of a hybrid of
Okay.
hip hop,
All right.
rock.
hip hop. Yeah.
I'll give it a
yeah.
listen.
Maybe not rap. Maybe
You've
hip-hop,
never
rock.
listened to the Beastie Boys?
No.
I'm going to make you a playlist.
You'll like that one. It refers not only
will.
to astronomy and planetary things, but Star Trek as well.
I'll definitely give it a listen.
Planetary.
I noticed that, speaking of Star Trek,
Oh, yeah,
right
Haley.
before the launch of Inspiration 4, Cyan Proctor was
Oh, yeah.
given the Vulcan salute, and she and Haley are both Trek fans.
Yep.
Excellent.
Some of the other folks were Battlestar. There was a whole thing
There's
of
a
which one do you
Battlestar
like.
fan and Star Wars
Yeah.
fan, but 2 Treks.
Excellent.
The sciencey people.
Anyway, let's trek on out to
Yeah. Let's
out
talk
of the
quasars.
galaxy.
Some of our favorite.
I've heard. You know what I
objects.
know about Josh?
What do you
he
know
likes
about Josh?
quasars.
I do like everything you've heard.
What
is
do you
true.
like? What do you like about quasars? Their name.
It is a good name.
I do.
It is an
like-
awesome name. It
I
sounds
do
cool.
like the name. It's a good abbreviation, sort of acronym kind of name.
Yeah.
And they're very, very energetic.
They're so energetic.
They're very powerful.
They really punch up the power.
Yeah, they
Yeah.
do.
Yeah,
I'm a
they're
big
crazy
fan of
because
them.
He's a
they're
big fan.
they're like, the for a long time we didn't know what they were. They're very, very bright things that we can see across the entire universe. Essentially, they're little objects. I mean, they're basically the black holes at the centers of young active galaxies, and
Then how
they're
are they so
brighter
bright?
often than the entire galaxy. I mean, like. They're typically on the order of 100 or sometimes 1,000 times as bright as the entire Milky Way galaxy.
Crazy.
And we know they're
one object.
We only see them at great distances.
Yeah,
So they're sort of
That's
an
good.
early universe phenomenon.
for the most
Is that
part.
a fair statement?
That's fairly fair. I mean, they definitely are more common the further back in the universe you go time-wise.
Is that why?
Because when galaxies were young, they still had lots and lots and lots of debris and stuff like that to feed that central black hole.
Hungry beast.
That hungry beast, right? Obviously, eventually, all that stuff that can fall in will fall in, and then galaxies calm down. And so,
It's sort of like as we were speaking recently about galaxies whose star formation is slowed to a crawl.
right.
And
Right. So this
there's that early crazy hungry phase.
right, and it's a very good thing, right? As Eddie suggests, because these things are very energetic, and if you were around in a galaxy where that's going on, you're going to find yourself in
I
trouble.
won't be near that.
You have a sunburn.
Yeah,
You
because
need SPS 10 billion. SPF.
yeah, these things are insanely bright, and they emit all over the electromagnetic spectrum. From radio and far infrared all the way up to X-rays and gamma rays, and so it's very bad news if you are nearby one of these things. But luckily, they're far away. Because they're so far away and so very bright, though, they provide some very unique opportunities for us in astronomy, not just to study them in their own right, but also as tools in like cosmology, right? Because we are desperate to learn about the universe when it was very young. These are
Very desperate.
strong signals from the universe when they were very young, when it was very young. And so they're awesome.
I'm sorry. I got to interrupt and ask a question.
Yeah.
So
Did I
they're
screw
very
something
far
up?
away. No, not at all. It's just a
are you
legitimate
sorry?
question because I'm interrupting him.
Oh, yeah, we never do that on here.
Would we would have a bad day if there was a quasar at the center of the Milky Way?
Yeah.
What about if there was a quasar at the center of the Andromeda Galaxy?
I think we'd be okay.
Okay.
It's maybe
Unless-
depending on which direction it was going.
So there's another thing about this. These things
They have those
do
jets.
spray radiation in every direction, but it's brightest
In a
typically along a certain axis, and so I'm not actually sure.
It might be a trivia for a future episode.
Yeah,
it is.
like
Yeah,
at
we'll
what
have to calculate
distance?
if you're in
Yeah.
if it was pointed right at us, if we'd be in trouble in Andromeda.
Okay.
I feel like we might be in trouble,
Yeah.
but I'm not 100% sure.
Intuition tells me I don't want to be there.
Yeah.
All right. So anyway, we don't need to worry about that, though.
No, we don't need to worry about that, luckily. Because even though Andromeda is, 2 million light years ish away,
Yeah.
that's the blink of an eye in the cosmic timescale, right?
Right. And it's not that far.
No, it's not that far.
It's a 25 Milky Way diameters away.
Right. The Milky Way is 100,000, light years across, and so it's not. I mean, it's further away than the edge of the Milky Way, but not crazy.
Not that
Crazy. Not
Not crazy.
astronomical distances.
Right.
Ironically.
Right.
So,
Quasars. Why are we interested in them today? Because we're finding out that they might be useful as another thing that Josh really, really likes: standard candles.
It's true.
he does like his candid.
Candors.
His candors.
His candle's very standard.
Yeah, you gotta have standard.
Just like
And
a
if we
white
remember,
taper.
a standard
Candles.
candle.
Standard. I love a white taper.
What's your other favorite standard candle?
The supernova.
A supernova. The Type 1A supernova.
I usually like rain or ocean scent candles.
I mean,
Those are nice.
I'll take a Cepheid,
Calming.
I'll take a Cepheid variable.
Cepheid variable, right? Those were the kind of the
I really
OGs, the
prefer
original ones, right?
Yeah.
A standard
Yeah,
candle is just
supernova.
something that we know how bright it is without looking at it. I mean, not without looking at it, but without
measuring how bright it is.
right.
Yeah.
We know independent of our measurement of its brightness how bright it is, and that means when you see how bright it is and you know how bright it is, then you know how far away it is.
Right. So it's like a light bulb that's a 100-watt light bulb that says, I'm a 100-watt light bulb.
Right.
Yep.
Right. Then you go look at it. If it's really bright in your face, you know it's bright. Anyway,
You know, it's
so yeah,
close. And if it's
exactly.
really faint, you go, dang,
Right.
You're a liar, light bulb.
you
Right.
must be really far away.
Because so these are critical to our attempts to find the distances to things far away. I mean, things that are nearby, it's reasonably easy to use geometry and things like that to figure out how far away, like
to
parallax angle and things like that for stars that are nearby. But how do we know how far far away the Andromeda Galaxy? I said it's 2 million light years. How the hell do we know that? We haven't been there. You can't use parallax or any of these funky geometry things. The way we know is
Standard
by
candles.
Cepheid
standard
variables.
candles. In that case, Cepheid variable stars, which are
I like those.
these are variable stars that vary in brightness in a very regular way that is related to how bright they are.
Right.
And so you measure how quickly it takes to go from bright to dim to bright again, and you know how bright it is. Now you can find one in Andromeda.
They're stellar strobes.
Yeah, they're stellar
And the
strobes.
frequency of the strobe relates to how many watts
How
they
many
are.
watts they are. And luckily they happen to be really, really bright stars, which
Right.
means that you can make them out in Andromeda and a bunch of other nearby galaxies.
Right. If you had any thoughts about like making a little light panel that said I'm 100 watts and holding it outside for alien astronomers wouldn't do any good because
Wouldn't
it's
do
too
much.
faint for them
Yeah.
to see it.
But if you had a Cepheid variable,
Cepheid
handy.
variable
Then
stars, yeah.
yes.
Yeah, those are hundreds of thousands of times, sometimes brighter than our sun, which makes them easily
bright.
visible in
Observable
distant
from other
galaxies.
galaxies.
Right.
Which
is
is
great.
wild.
That is wild. But still,
The universe
only
is just wild.
It is wild.
Yeah.
But only so good because
Wild and crazy.
we can
universe.
see one in Andromeda. We can see them in a bunch of nearby. But if the galaxy is too far away, then even 100,000 times the brightness of the sun is too dim. I can't see that individual star.
Right.
So we need even better, not better, but brighter standard candles.
How about quasars?
And the type 1 supernovas you were mentioning are one, but then you have to get lucky because,
they have to pop off
in the thing.
Then they're gone.
And it's useful, and that's great. But what if we had even more? And it turns out that we might be able to use quasars as those things. We're finding out because there's a relationship. Because like I said, quasars let off light in every part of the spectrum, but they let off a lot of ultraviolet and they let off a lot of X-ray for some very particular reasons.
Interesting.
And the relationship between how much X-ray and how much UV they give off turns out to follow a nice, simple rule.
Ooh.
And it's a simple rule that doesn't depend on how far away the quasar is.
Okay.
That's important because it could be that quasars early in the universe had a different relationship than quasars later in the universe, but they don't seem to have that.
But I thought, weren't we already sort of figuring? Isn't the whole one of the cool things about quasars that we sort of already know how far away they are because they're so far away that they're cosmologically redshifted away.
They are.
But you can distinguish between like z equals 1 and z equals 3 maybe.
Well, we can do that. So the point is we want to be able to measure the distance independent of that to test.
To verify the cosmological expansion.
To understand how fast the universe was expanding back then, for example.
So we look at it and we say, okay, well, it's redshifted z equals 1, for example.
Right.
And then we're sort of using some assumptions to say z equals 1 equals 3 billion light years, or whatever that number happens to be. So this would enable us to say, actually, it turns out z equals 1 is 2.5 billion light years.
Well, for that, or if I could say that particular object, that has z equals 1 is such and such a distance, that I know the universe was expanding faster back then, or slower or something like that, right? And so we're desperate for independent distance.
We are desperate.
Desperate for independent distance measurements, and they're really, really hard at those distances.
Yeah.
But quasars, being so ridiculously bright, if we can standardize that candle, man alive, that's going to be really awesome. And it turns out.
And it's kind of like, it's also sort of the only game in town.
Right.
It's kind of,
right.
What else is it going to be?
Good.
Right. It's right. At these distances, right.
That's the only thing you can see.
It's the only thing you can see, basically. And so, but luckily they seem to be behaving themselves. And as long as we understand this relationship between the UV light and the X-ray light, and as long as it's fairly standard in all quasars, then...
Okay, so how is it, though... all right, so you see a ratio of visible to X-ray.
Right.
But how do you know...
UV.
UV and X-ray,
UV and X-ray. So you have this ratio of ultraviolet to X-ray, and then you can say that that's correlated somehow with the actual wattage of the quasar. But how do we know any of them? How do we know how do we calibrate?
Right, so you have to calibrate it, which means that you have to be able to...
You have to see one quasar that you somehow independently know how far away it is.
And luckily, not every quasar is at like the actual edge of the universe, right? There are quasars that are nearby. So this is like any of the kind of steps in our distance ladder in astronomy. There has to be some overlap so that you can get, and it was the same thing with Cepheid variable stars. Like before we did that, we had to independently measure the distance to a few of those. Luckily, we have some in our neighborhood. Polaris, for example, is a Cepheid variable star. Polaris is a Cepheid variable star.
I didn't know that.
And so because of that overlap, we could, and in fact, that's why they screwed up the Hubble stuff in the very beginning. They didn't have the Cepheid variable relationship right, and so they were measuring the distance of all these galaxies wrong, and so they radically misunderstood the age of the universe and stuff like that in the very early days. But anyway, now we've calibrated that well. This needs to be calibrated, of course.
But there is an overlap. There are quasars close enough that we can independently say this thing is that far away, and therefore we can measure its brightness and know how bright it really is.
Right.
And there's enough of those that then we can do this UV.
We think we're trying. It's not this. We're in the early stages of doing this, but we're pretty sure this is working. So this is pretty cool.
That's exciting because it involves quasars and stuff.
Quasars.
Yeah. All right. So, how fast was the fastest meteoroid based on my extensive Googling of about 15 minutes going when it entered the Earth's atmosphere? Bonus points if you know anything else about the impactor, like its mass, or that's about it.
I'm sure I know less about this than Eddie, so I'll try and go first. so that I don't cheat using her.
Big old blank.
Oh, wait. The first thing you said, the fastest.
Would you prefer to initially? We can do it if you would prefer. I'll do the other two questions that will give you the range within which your answer must fall.
And those are based on physics, so we should
Those
be
are
able to
based
get
on physics.
No, but I can't.
What's the slowest speed? Based on simple arguments, nothing fancy, special cases or whatever.
Mm-hmm.
But what's the slowest speed that an interplanetary object can hit the Earth? So we'll do that one first.
10 kilometers a second.
Yeah, I was going to say 11.
Addie wins. 11.2 is escape velocity from the Earth.
Yes.
So,
knew
and that's. I, mean,
I was rounding. I was doing order of magnitude.
That's fine. You both
We're the
win.
same.
Okay, so that's fine. And I'm sure you could do some funky three-body stuff where it can come in slower or something like that.
Right.
Probably.
Right.
What's the fastest that an object could hit the Earth in principle? Again, not doing anything strange, but the limiting thing being it must be interplanetary and not
Right. Got to be
on
bound to the
escape
sun.
velocity from the solar system.
I don't know, Addie.
30
Kilometers per second.
kilometers per second.
500 kilometers a second.
Well, Addie's gonna win it, but 30.
Not nicely.
Yeah, that's okay.
Okay.
30 is the orbital velocity of the Earth, so that's a key number in the calculation.
Yeah.
Mm-hmm.
But you can imagine that you could have something on the same orbit as the Earth going the opposite direction, which
So
immediately gets you to
60.
60. But then you could also put it on an eccentric orbit so that it's going faster when it's at the Earth. And then you add in gravitational acceleration from the Earth, and you get up to 73.
73. Oh, okay.
Okay.
I was.
Okay.
So
She was right order of magnitude again.
That's like an Oort cloud comet coming in opposite
Yeah.
the Earth with a perihelion at the orbit of the Earth, traveling in the opposite direction exactly. You get
I'm just
73.
pretty excited that those two numbers were in my head. The 11.
That's awesome.
30.
That's pretty good.
You got it.
Yeah.
So the answer to the main trivia is
Gotta be.
therefore in between those two numbers.
In between those
11 and 73.
two. Okay.
It's got to be 42 then.
65.
Only 28.6.
Aw,
Oh, yeah.
that's pathetic.
Well, not a lot of stuff is coming in on opposite orbits. Most things,
No,
if
right.
you would
Most things
take an
orbit around.
introductory astronomy course, you would know that most things orbit the sun in the same direction.
But I thought that the fastest one would have been an example of one that was on a
It's not to
retrograde
say
orbit.
that something faster hasn't come in, but were you looking? You know,
Right.
were you recording and measuring that or whatever? So this was in 2012. It left a meteorite called the Sutter's Hill meteorite. It was near Lake in Nevada.
I've heard of that one.
Yeah.
I didn't realize.
The object was probably a few meters across
Wow.
when it came into the atmosphere. Yeah. So final bonus trivia. How fast was that Sandia National Labs bullet going that they fired a 1 gram bullet from a 60-foot long gun? What do you think?
1,500 kilometers per second. Is that stupid?
I think so.
It is stupid.
Thanks.
I had to stop
Yeah.
myself.
Is
from
that
giggling.
really?
But I can't giggle because that is so much closer to the right answer than I got to your trivia on the last episode. So I'll never be able to make fun of anybody's wrong answer.
What was.
Ames was 7,
Yeah.
and then the dust accelerators get up to like at most 100.
100.
So that's kind of a clue.
Okay.
And that's for a really teeny tiny thing.
I in my head I got confused. I thought I remembered 1,000, and so I was from the beginning. So that's why I said
No,
yeah.
100.
okay.
I'm going to go with 73.
Oh, that's fun. Well, why not? But
Yeah.
no, it's only 16
Oh.
kilometers per second.
Oh.
So
pretty fast.
that's-
Still pretty fast for a 1 gram thing.
Yeah, you have to think humans have gotten things going faster than that,
Yeah.
but it's with continuous acceleration, continuous thrust. And the key thing here is this is an impulse,
So is
basically.
Punched
is that gun like a gas expansion thing, like a typical gun, or is it like a rail gun using electromagnetic stuff, or what?
I knew this at some point, but I don't remember now. I don't think it was an electromagnetic acceleration railgun. I think it was a gas, but I think it was a multi-stage thing where it gets accelerated to a certain point at one point along the muzzle or tube that it's traveling down, and then there's some additional.
Yeah.
So it may not have been a single impulse to get it going that fast.
Right.
But I
still,
think it was a gas
I guess.
expansion. But I'm not.
That's still
100%.
pretty cool. That's greater than escape velocity. It's just shooting a thing and it would just leave. I mean, assuming there was no...
if you got out of the atmosphere. Right.
Assuming there's no air resistance. Yeah.
Yeah. Well, while it may have felt like getting hit by an interplanetary impactor, it was just another episode of Walkabout the Galaxy. Give us 5 stars. Give us 5 stars. Then create a bot farm to give us 5,000 more.
Yes.
Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Drusik. Production assistance is provided by Diego Rodriguez. Thanks to our listeners in the Netherlands and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the AstroCork, signing off until the next episode of Walkabout the Galaxy.